Have you ever wondered why finding the slope of a curve and finding the area under a curve, two problems that seem to live in completely different worlds, turn out to be exact opposites of each other? By the end of this video, you'll see the one picture that makes this obvious, and you'll never look at an integral sign the same way again. Let's start by building something called an accumulation function. Picture a curve f of t and shade the area underneath it, starting at some fixed point A and running up to a variable point x. We call this shaded area a of x, the integral from a to x of f of t dt. Now watch what happens on screen as we nudge x forward by a tiny amount, h. The new area, a of x plus h minus the old area, a of x, is just the thin sliver of region between x and x plus h. We'll look at this sliver both flat on the page and tilted into a three-dimensional view, so you can see it's genuinely a thin vertical strip under the curve. If h is very small, that thin strip is almost a rectangle. Its width is h and its height is roughly f of x, the height of the curve at the point we started from. So the area of the strip is approximately f of x times h. Here's a moment to pause and think for yourself. Using that thin strip picture, what do you predict the quantity a of x plus h minus a of x, all divided by h, approaches as h goes to 0? Have a guess before I reveal it. Divide our approximation by h and the h's cancel. The quantity a of x plus h minus a of x divided by h is approximately f of x for any small h. So in the limit, as h goes to 0, this ratio approaches f of x exactly. But that ratio is precisely the definition of the derivative of a. So we've shown derivative of a evaluated at x equals f of x. This is the first part of the fundamental theorem of calculus. The accumulation function a of x always has derivative equal to f of x. In words, differentiating undoes the process of accumulating area. Differentiation and integration are inverse operations. Now let's use this to get the second part of the theorem. Suppose f is any antiderivative of f at all, meaning derivative of f equals f of x, just like a. Since a and f have the exact same derivative everywhere, they can only differ by a constant. So f of x equals a of x, plus some constant c. To find c, plug in x equals a. We know a of a is 0. Since the integral from a to a of anything is just 0, the region has no width. So f of a equals 0 plus c, which means c equals f of a. Now plug in x equals b instead. We get f of b equals a of b plus c, which is a of b plus f of a. Rearranging, a of b equals f of b minus f of a. But a of b is, by definition, the integral from a to b of f of x dx. So we land on the second part of the theorem, integral from a to b of f of x dx equals f of b minus f of a, where f is any antiderivative of f. Before we plug in real numbers, pause again and make a prediction. If f of x equals x squared and we integrate from 0 to 3, what number do you think we'll get out at the end? Keep that guess in your head. Let's verify both parts with a simple example. Take f of x equals x squared. An antiderivative of x squared is f of x equals x cubed divided by 3, since the derivative of x cubed over 3 is x squared, matching f of x exactly. First, let's check part 1 directly. The accumulation function here is a of x equals the integral from 0 to x of t squared dt, which works out to x cubed over 3, the same as f of x, up to the constant we expect. And sure enough, derivative of x cubed over 3 is x squared, confirming derivative of a equals f of x. Now for part 2, we want the integral from 0 to 3 of x squared dx. Using our formula, this equals f of 3 minus f of 0. f of 3 is 3 cubed divided by 3, which is 27 divided by 3, which is 9. f of 0 is 0, so the integral equals 9 minus 0, which equals 9. If your earlier guess was close to 9, well done, you were thinking like the theorem. So there we have it. The slope of the accumulation function gives back the original curve, and the total area under that curve is just the antiderivative evaluated at the endpoints, subtracted. Two seemingly separate ideas, slope and area, turn out to be perfectly matched inverses. If this finally made the fundamental theorem click for you, hit like and subscribe. It genuinely helps this channel grow. Next time, we'll take this same idea and push it into 2 dimensions, exploring how the same logic gives us Green's theorem. See you there.